Okay, hi everyone, good afternoon. I'm Marlon from openEuler community. So in openEuler, I'm responsible for the embedded and the edge scenarios. I'm the member of technical communities. So today, I'm so glad to be here to introduce first time in overseas, openEuler embedded, an open and comprehensive embedded software platform. So this is my agenda today. There are two parts. Part one, I will take a quick review of openEuler embedded, including what it is, the general architecture, key features, application scenarios, and some cool demos. Then in part two, I will want to make a further discussion of a very, very important technical feature of openEuler embedded. We call it MICA, the Mixed Criticality Framework. Okay. So thanks to Dr. Xiongwei's sharing in the first half, I think that everyone here already have a basic knowledge about openEuler. Here I want to make a quick review. So as we know, openEuler covers four main scenarios: server, cloud, edge, and embedded. Well, server and cloud started from December 2019, and edge and the embedded joined in since 2021. We are little brothers in openEuler's family. And openEuler, with four scenarios, openEuler not only covers ICT technology, it also covers OT operation technology through openEuler embedded. And facing so different scenarios, what makes openEuler so different is that in all four scenarios, we share everything that can be shared. For example, we share the same kernel versions, we share most of the main software package, and we share, of course, CVEs. And so all software packages, including kernel, are maintained in Git repo. And we also have mirrors in GitHub. And different scenarios are created and released through the compose system. Currently, for cloud and server, we are using OBS. And for embedded, we are using Yocto, but we have a plan that maybe in future, maybe 3 or 5 years, we will evolve to the Aura Maker. Okay, next, after more than 2 years grow up, and we now have a clear definition and position for openEuler embedded, an open and comprehensive embedded software platform. So why do we have such a definition? There are some backgrounds and trends I want to show here. So from application viewpoint, embedded system, embedded application are becoming more and more complex. Rich features, AI, more connectivity, AI and IoT connectivities. So these complex features requires complex software platform to support it. This is one hand. On the other hand, thanks to Moore's law, currently, and embedded hardware is more and more powerful than before. You know that 10 years ago, we talked about the embedded systems. They are 32-bit microcontroller, but now we're talking about the embedded systems. They are SoCs. They are used a lot of areas like mobile phones, like smart vehicles. So I mean that strong and powerful hardware provide a physical, solid foundation for a complex software platform. So this is the background. And with this background as the de facto standard of a complex embedded software, Linux, we can see is more and more popular in everywhere. Start from mobile phone, now smart vehicles, and even to satellites, industry controllers, which are areas which we view as traditional embedded systems, right? But I want to mention now here is Linux is powerful, but it's not the one embedded system. You can get rich features. You can get good connectivities, but you can't get some inherent characteristics of embedded system. For example, real-time, safety, reliability, low power, because Linux kernel is not designed for that, right? So therefore, we define here openEuler embedded is a Linux-centric, comprehensive, and open embedded software. Here, and Linux is important and necessary, but not everything. So you can see this architecture, openEuler embedded just like a solar system. Like a solar system, and the sun is the Linux is provide most of of functions. But we also have non-Linux systems, non-Linux plugins. Like if you want to have hard real-time, you can have real-time operating system. If you want to have good security, I think you need something like TEE, TFM, and Trust Zone, right? And if you want to have extreme performance, so you want to, you didn't want anything, you just bare metal, right? And if you want to good reliability, you will need embedded virtualization, like embedded hypervisor to do that. So as the sum of the solar system and openEuler embedded provides gravity with the infrastructure, tools, and some key features like Mika, I will discuss later, and the soft bus, yeah. And different plugins provide their own characteristics and features and ecosystem. For I just mentioned, if you need a hard real time, if you want to use in controller, you must have a real-time operating system like Zephyr, like NetX, like ThreadX. Okay. So this is the openEuler's architecture, from down to top. In hardware, we have more diverse hardware, and then server and the cloud. And in application, as I just said before, openEuler embedded is facing for the OT scenarios, so you can find the PLC, reverse energy, right? So for this application I just mentioned, we are not owning one OS, it's a collection of OS, and Linux for some complex functions. And if you want to some critical functions, you need the real-time operating system or even bare metal. And here for real-time operating system, we don't have a unique options. You can choose, depends on your need. For example, you can choose Zephyr, and you can choose ThreadX. And in China, Thread is very popular. Oh, no problem, you can choose it, right? And the Fusion Dock and Mika are two technologies to supporting the running of multiple OS running together, which I will discuss later. And for DFX and tools infrastructures, there are some parts which will be easily ignored because if you have embedded system guy, you know that the debug and the trace and performance tuning in embedded systems is very hard. We don't have powerful tools like what we have in server and the cloud, right? So this is the part we will focus on. And as a platform, open source platform, infrastructure is very important. It supports our daily work, right? And openEuler's key features can be summarized as 1 plus x and 1 plus x plus 1. The 2, 1 are just like two legs of one body. They are invariants. They are supporting, the whole bodies. One is we want to build a high-quality embedded Linux framework based on the openEuler community. And to support this, we should have good infrastructure like CI, repos, build, CI/CD, SDK, simulation, a lot of things, but maybe not shiny as runtime features. And above two legs, there are X. X means they can be changed, right? And we start from soft bus. Soft bus is kind of a networking connection technology, just to connection nodes, right? It's something like the Matter protocol, but it comes from China, comes from our brother community, OpenHarmony. So we bring it from OpenHarmony to openEuler, and we want to try to use it to connect the openEuler device and the OpenHarmony device. And next mixed critical systems I will discuss in part 2. And the embedded robot runtime is a robotic framework. It's a framework for robotic applications. So we integrate those two. So you know that if you are those two guys, you have those two applications, most about Ubuntu. But now openEuler provides a second option. You can develop those two applications fully in openEuler from the development to the runtime. And one leading university in China and contribute their work on industrial robot to openEuler. And we also integrate some technology from RTOS like micro-loads and together to support the requirement on real-time safety and reliability. This is embedded robot runtime. And the embedded edge and the embedded AI are two new areas that we focus in this year. And for AI, there's no I don't want to say more because it's so hot. We need to support it, right? So we will try to integrate the well-known AI framework like TensorFlow-Lite, like PyTorch, like MandoSpore. This is the basic work. Then we will go further. We will try to explore the topics like, for example, real-time AI, like resource optimization, right? And in the embedded edge, we will try to, you know that the embedded area is a very traditional area. They don't like new features, right? But we will try to bring an IT-related technology like containers, K3s, EdgeX into embedded. We want to make the architecture, cloud, edge, and node framework more efficient. Okay. So besides these features that we are working on some upcoming features, for example, eBPF, Rust, and whether we will put it into our task list depends on the requirement of need and the resource what we have. Okay, so this is the openEuler embedded key features. Next is the running models of openEuler. There are 4 models: single model, MP model, virtualization model, and the fusion models. And the single model is the most popular one. You just have one OS to fix most of the problems. But as I said, if you use embedded Linux, you can't get real-time safety and reliability. So the other 3 models are designed for this. The difference is that the AMP model is more suitable for hardwares, heterogeneous hardwares. And the virtualization model is more suitable for homogeneous hardware, but with hardware virtualization support. And the fusion model, the most complex one, I think it represents some kind of trend in the future. It has everything, right? Okay, with running models, we can deploy openEuler embedded in these scenarios. So you can deploy it in server. If you want to, for example, if you want to design a centralized controller, so you can have a server, and the server version, you can have openEuler embedded. For management, you can have RTOS for real-time control, and the RTOS will connect with device through some real-time network like EtherCAT, like Ethernet IP, whatever, TSN, and in edge-based, okay, and in node-based. So here I want to show the ecosystem of openEuler embedded. First, our Linux part, like the kernel, software package, and the infrastructure, we are set up about openEuler community. So our build system coming from Yocto, right? So we have Yocto's ecosystem, but we have a big goal. Maybe in the future, we will have our own unified build system, Euler Maker. So we have non-Linux planets, planes, and in application layer, we are facing for industrial IoT, robotics, energy, BMC. BMC is an embedded device in server. So here I want to take in Zephyr project as a good example for cooperation. So we set up a SIG Zephyr in openEuler. SIG means special interest group, and through SIG Zephyr we want to do the introduction and promotion of Zephyr in China because it's a global project, but not so popular in China. So we want to SIG Zephyr as a bridge to.
I don't think Zephyr is not popular.
Because in China, there are so many IoT projects. Benjamin knows that, right? So we want to bridge to connect openEuler and Zephyr. So for Zephyr, I mean, openEuler is a good local partner to set up a Zephyr ecosystem in China and accelerate the promotion and the usage of Zephyr. And for openEuler, as I said, we are a big one, right? But we need a high quality of little OS to working with openEuler. I think that's also the definition of Zephyr with Linux in Linux Foundation, right? And also Zephyr is a good partner to go to the globalization process of openEuler. But as I said, it's not limited to Zephyr. Maybe we can work with Eclipse, NetX, Eclipse ThreadX, and Apache NetX. So we have some joint events in ZDS last year, this year. We will have some talks in ZDS, and we also invite Zephyr to join openEuler's events like ODD, like MWC workshop today. And we also have some technical achievements. For example, we have an innovative program called Zephyr-based virtual machine. Right, this is coming from openEuler from China. and we want to, maybe in the future, we donate it back to the upstream, right? We also, the 6 Zephyr member also contribute Raspberry 4B rock trip support in Zephyr, right? So this is the architecture of ZVM is coming from a member of openEuler, the Hunan University, and it will be incubated in openEuler's 6 Zephyr. So this is some interesting application demos in our last openEuler summit. You can see that industrial controller solutions. Okay, we have integrate openEuler embedded with EtherCAT to control servers. And this is the mobile robot solutions. It runs those 2 Mica and the lightweight component and the soft bus. Is used in the electricity area. And we have openEuler embedded in the UXV solutions, robot arm, robot dogs, and the UAVs. And this is also a typical solution in the server scenario, a BMC, the broad management controller. And we also launched a very interesting project named Euler Arm, and we use it to paint, right? Okay, in part 2, I want to make an introduction about the Mica, a very, very important feature of openEuler, just mentioned by Dr. Shongwei. So I will make a detailed discussion about it. So the background of Mica.
So detailed. You always spend too many time.
Yeah, that's right. That's right. The background of Mica, in fact, is mixed critical analytic system. Is a concept from academic, right? But I think in academic critical analytic mainly refers to the safety levels like ACL ABCD and CO2 3. But I think that we can extend it to other critical areas like real time, like power, or whatever. So this is a trend. One trend is from distributed to centralized. A good example is some smart vehicles, okay, from ECUs to domain controller to central controllers. And we also found it in industrial areas like the idea of VPLC and cloud PLC. And we also find it in node device because node devices are becoming more and more complex, right? This is the architecture of Mica, and to summarize, it's running about multi-core SoC. It has multiple OS instances. So we have Fusion Dock and Mica to support it. Okay? So we defined, in our strategy, we defined 3 phases. Phase 1, deployment, then quarantine, and phase 3, scheduling for better efficiency, better utilization of resources. Okay, this is the further introduction of a Mica framework. Two core components. One is a Fusion Dock. Fusion Dock is not a one technology. It's a collection of technology, including virtualization, lightweight container, LibOS, heterogeneous, whatever. And Mica is our core part. It will have four core functions: life cycle management, like containers, and share memory-based high-efficient cross-OS communication, and the service framework, and very important part, multi-OS build infrastructure. We want to build it in one shot to have a lot of OS image in one image. Okay. So this is our load up of Mica. Dr. Shong just the slideshow is our startup. We just did it in 2022. We based on openMP. We just do a proof of concept. And in these 2 years, our focus is on virtualization based from KVM plus Priority, then parallel virtualization, then go to real-time virtualization. And we are also show a lot of focus on the infrastructure, like Unified Build, SystemDTS, and DFX. Right? And user space solution, we are also trying to do some work, but it's middle priority. So we want in the future, maybe next year, we want to have a very comprehensive and solution. So we call the heterogeneous multi-core MCS. It will be include openMP, real-time virtualization, lightweight container, and KE. So very complex. So this is the demo, joint demo that we're working with Intel. That you can is running above powerful Intel hardware. There are 12th and 13th Intel core platform. It has a lot of cores, and then above a lot of cores, you can find went to other service image windows for HMI, RTVM, openEuler embedded based to do some work, and RTOS VM based on Zephyr is very complex. Okay, so thanks. This is all my sharing today. We can have further discussion later.